Record myself.
Doctor.
Yep. Yes.
Good afternoon, Doctor. I have a question about our finals. It's about the difficulty level of the papers. Do we expect it to be like our test, the difficulty, or like assessment one?
Oh, assessment one lagi.
This is just an expectation, Doctor. Like what we should expect lah.
So assessment one, I think it was harder than your test one, but test one is not easier than your MCQ and then your quiz, right? Your quiz is much more simpler. So I would assume, the way that when I saw the question, I think it was similar. The difficulty is similar to your test one. Okay, so some of you will get an A, some of you will get a B, some of you will get a C. But hopefully everyone gets an A and B. But the difficulty is like that. Okay, tak adalah macam nak failkan semua orang. So it's like average difficulty. So that some of you can do it really well, some of you will do average. Macam itulah. Not that hard like assessment one. Assessment one, everyone failed. Almost everyone failed. Okay, so we don't want that. So that's why we redesign. When we are designing questions, we have to think of you guys. What is the level that we can test you on? So from assessment one, we did not go through the questions together, so that was the mistake there. Okay, so that, but it's okay, it's 5%. You guys did so much better, and your assignments and your lab marks will cover for that, so no worries. Okay, so physics ni, the way that our unit is, our mindset lah, I would say that the mindset of my colleagues is, we don't want to make it very easy for you to get an A, but we don't want to make it easy for you to fail as well. So we want you to be in the middle. Okay, so if you get an A, that's excellent. Okay, but we are designing so that the average people will get average marks. Macam tu. Okay, so tak adalah fail. Alright. So please just do your best.
Thank you, Doctor.
Don't think too much about it. Just do your best and that will be okay. Okay. Alright, so for chapter 12, I will be skipping thin film interference. That's not going to be on your exam. Diffraction grating is not going to be on your final exam as well. On your quiz, only covers this part, these 3 subtopics only as well. So the quiz akhir tu, dia punya chapters and the topics are the same as your finals. Okay, so please prepare the same topics lah. Okay, prepare on the same topics. Okay, let's do this. So after completing this chapter, you should be able to explain the interference of waves, double slit interference, not this part, yes, this one, and not this one. Okay, so diffraction grating and thin films, we are skipping that one. You can read that on your own time. So waves obey the superposition principle. We know this. I've talked about superposition principle. It just means that it overlaps and adds up together. So if I have a wave that looks like this, and there's another wave that also looks similar to it, when the peaks meet with the peaks, am I recording? Yes. When the peaks meet with the peaks, it adds up and becomes a higher in amplitude. And this guy throw meets with the throw, so it becomes a lower amplitude over here. So it becomes higher lah. So it adds up just like math. So if this guy is 10, this guy is 10, this guy becomes 20. This is minus 10, this is minus 10. This becomes, hello, where are you? Minus 20. Okay, so it adds up. Superposition is just adding up 2 waves together. But the adding is called superposition principle. So there's a name for it. Okay. Adding together the displacement, that's what we did. 10 plus 10, 20. Minus 10, minus 10, minus 20. So if I have a wave that looks like this is my first wave, and my other wave looks like this, by the superposition principle, oh wait, it's not exactly correct. By the superposition principle, this is 10, this is minus 10, they add up together to become 0. This guy is minus 10, this is 10, they add up together to become 0. So what happens? What is the resulting wave? It's just a straight line. It's just nothing, it's nothing, it's just 0. Okay, so this is true for waves. Right, so now we are talking about phase angle and phase difference. I've mentioned about phase before. I think in chapter 9, I think. So phase is the difference in time. Difference in time between two waves. Between two waves. Okay, so let's take a look. To find out what is the phase difference, first I need a reference wave. So this will be my reference wave. It can be any wave. It can be a cosine or sine. It doesn't matter. As long as you say that it's your reference wave, that is your reference wave. So in this case, this is our reference wave. And I want to compare this wave with my reference wave. I am comparing my wave with my reference wave. So when I compare it, I can see that the difference between these two waves is 2 pi or 1 lambda. How do I know it's 1 lambda? Because one wavelength is when it starts to repeat itself, right? So it starts to repeat itself when it reaches this point. So that is 1 lambda. So that is 1 lambda, which is also equal to 2 pi. So 1 lambda is equal to 2 pi. 1 lambda is 1 wavelength. And this guy is in radians. So 1 wavelength has 2 radians of cycle because it's 1 complete cycle, 2 pi, right? 1 complete cycle, 2 pi. 1 complete cycle, 2 pi. So that is what it means. Now, when this guy, I'm comparing these two guys together, right? Two waves together. And I see, oh, this second wave starts earlier by 2 pi. Starts earlier by 2 pi. If it starts earlier by 2 pi, my equation becomes positive 2 pi. What is this? This is called phase difference. Okay, so it just means that my wave, that Y2 wave, starts earlier by 2 pi. Okay, the same thing if my wave starts earlier by pi. So it starts earlier by pi. How would that look? It looks like this. Let's use a different color. If my wave starts at pi, starts at plus pi, okay, so my wave would look like that. So now the difference between the top and the bottom wave, the blue wave and the reference wave is just pi. What is pi? Pi is half a wave. So half of lambda is pi. Okay, just throwing that out for you. So sama je 1/2 bagi 2, so dapat pi. Okay, so it's the same thing. So now the difference between the blue wave and the reference wave is pi. So how does my equation become? It's A sine kx minus omega t. It starts earlier, so it's a positive pi. That is Y3. This guy is Y3, this blue guy. Okay, so let's take a look at this. This is Y3. So let's say this is Y5 lah. I'm confused. This is Y5. Okay, so let's take a look at Y3. This guy is Y3. It starts later by pi, but it is flipped. So it shouldn't be like that. It should be negative. Okay, yang kalau dia nak cakap minus pi, it should start like this. Oops. This is how it should look like. It starts later by pi, but the shape should be the same as the reference. Okay, so it starts later, maksudnya this is our reference. Dia lambat by 1 pi. When dia lambat by 1 pi, this becomes minus pi. Dia lambat by pi, so minus pi. The wave should look exactly like our reference, but it starts later by pi. So it's a minus pi. Okay, so when we are talking about these pi's, we are actually saying the phase difference. We are actually talking about the phase difference. Okay, so that's the first term that you need to know, phase difference. Okay, this guy is called phase difference. Walaupun example dia salah, let's not use this one. Yang ni betul. This is phase difference. So what is the notation for phase difference? We use this guy. It's called phi. Looks like this. Oops. It looks like that. So it's called phi. Okay. Phi. So that's your phase difference. Phase difference is in radians or in pi's. Okay. Next one. Now we talked about phase difference. Now we are talking about path difference. So phase is in radians, path is in distance or in meters. Okay, so what is path difference? I told you earlier that this 2 pi can be equated to one wavelength. If you have 2 pi of difference, it just means one wavelength of difference. If you have a pi difference, just means divide by 2. So this one divide by 2, 1/2 lambda difference. Lambda is in meters. So if you convert the phase difference to lambda, you will get the path difference. Okay, so for example, I have this much of phase difference. What is this? This is, if this guy is pi, half of this will be pi over 2. So my phase difference between, comparing it to the reference wave is pi over 2. So how do I translate this into path difference? This is phase, eh? How do I translate the phase difference into path difference? Simple. I know that 1 lambda is equal to 2 pi. So if I want pi over 2, I need to divide this by 4. Sekejap, berapa? 1, 2, 3. Yeah, divide by 4. 4 parts. To divide this by, I need to divide both sides by 4 to make this guy pi over 2. So it's the same, right? So this guy becomes pi over 2, which means that pi over 2 is 1/4 lambda. Okay, so that is my path difference. If I know what is my lambda, for example, it's 570 nanometer, I can plug that into here and I can know that my path difference delta L is 1/4 570 times 10 to the minus 9 meter. So that is my path difference. Okay, so what is phase difference? Phase difference is in radians. It tells you whether it starts earlier, so that's a positive. If it starts later time than the reference wave, you get a negative sign. Phase is always in radians. It tells you when the starting point of the wave is. Okay, whereas path difference, it tells you the distance, the difference in distance between the first wave and the second wave, that is in meters. You can convert phase difference into path difference by this equation. 1 lambda equals to 2 pi. This guy is in meter, this guy is in radians. Okay, so just convert that to become path difference. Everyone okay so far?
Yeah.
Okay, so phase is the starting point. Path difference is the perbezaan dari segi distance. Okay, so phase difference is in radians, path difference is in lambda or in meters. Lambda is in meters as well. Okay, so we have two things that we talked about, phase difference, path difference. Now we are talking about waves in phase. What does it mean? Waves in phase happens when the difference is, oh, it's here. Waves are in phase when the phase difference is plus minus 2 pi. It's a full circle. Maksudnya full lambda lah, or equals to 1 lambda. When the difference is 1 lambda or plus or minus 2 pi, it is in phase. Why is it in phase? Because if I'm looking at this point in time, let's say it's this guy starts, this is like, I'm just looking at this point lah. I'm just looking at that point in time and I see that these two waves, oh, they start at the same time. Padahal, wave number 2 started earlier by 2 pi. But I did not see that because I'm only looking at this point. So at this point in time, I'm looking at it and I see that, oh, these two waves start at the same time. So they are in phase. Okay, so they start at the same time, which means that the peaks will align with the peaks, the trough will align with the trough. So what happens when they are aligned? Constructive interference happens. Constructive interference happens. So when does this happen? Only when the difference is 1 lambda. Only when the difference is 1 lambda or 2 pi. The difference should always be 1 lambda or 2 pi for constructive interference to happen or for the waves to be in phase. Okay. Okay, so that was when it started earlier by 2 pi. So that's a positive pi. What about negative 2 pi? The phase difference is negative 2 pi. My wave number 2 starts later than the reference wave. So my equation becomes minus 2 pi. That's my phase difference. I have a phase difference of...
Doctor?
Yep.
Doctor, does it have to be 2 pi? Can't it be 4 pi, 6 pi, or won't it also be the same?
Yes, it's the same. Nanti kita akan cerita pasal ni.
Okay, thank you, Doctor.
Okay. So as long as it is, to answer Bella, as long as it is a multiple of lambda, an integer multiple of lambda, then it will be in phase. Sekejap, eh? What? No, I'm teaching. I talk to you later. What do you want? I cannot. I'm teaching. I really go eat ice cream. Ask auntie. Okay, sorry about that. So to answer Belle's question, it can be a multiple, an integer multiple of 2 pi or an integer multiple of 1 lambda. So nanti kita akan cakap pasal ni. Kita akan summarize this equation later. Okay, so please know that whenever that it has a difference of 1 lambda or 2 pi, it will be in phase, the waves are in phase, constructive interference will happen because they are aligned with each other. The peaks align with the peaks, the throw aligns with the throw, so they add up. So it's a constructive interference, right? So this is another example of waves in phase. This is when the difference is 2 pi, we talked about that. This is when the difference is 4 pi, so it's 2 lambda. So as you can see, if I'm looking at this point in time, I can see that they start at the same time. Where yang sebenarnya, in reality, this guy started way earlier than Y2 and Y2 started way earlier than Y1. But if I'm looking at this point sahaja, I can see that they are aligned. They start at the same time. Macam je lah, tapi sebenarnya tak. So when that happens, the waves are in phase. When does that happen? Constructive interference happens when the waves are in phase or the difference in phase is a multiple of 2 pi. This is it. When the phase difference is a multiple of 2 pi. 1, 2, okay. So what does multiple of 2 pi mean? Multiple integer of 2 pi. Kalau ni math punya expression kan. So if I were to say this in a sentence, it's a multiple. Is it integer multiple or multiple integer? Integer multiple. It's an integer nombor multiple of 2 pi. So maksudnya apa kat sini? Integer multiple is m times 2 pi. So kalau m kosong, kosong. M1, 2 pi. M2, 4 pi. M3, 6 pi. Which is the same, right? So m can be 0, 1, 2, 3. So if m is 0, you get 0. If m is 1, you get 2 pi. If m is 2, you get 4 pi. So on. So this is called integer multiple of 2 pi. Yes, ada soalan ke? No question? Someone unmuted tadi? No, okay. So this is called integer multiple of 2 pi and this is called integer multiple of pi. Of lambda, of the wavelength. So m times lambda. If m is 0, lambda is 0. If m is 1, lambda is 1. And m is 2, lambda is 2, and so on. Okay. This is m to 2 pi. Buang jap. This is 2 pi m. Okay, so the phase difference should be a integer multiple of 2 pi, or the phase difference should be integer multiple of lambda. So that will make your waves to be in phase and constructive interference will happen. Okay, now we are talking about waves that are out of phase. What is that? It is when the peak meets with the throw. And when does it happen? When your when the difference is pi, when the phase difference is pi. Okay, when your phase difference is pi or half a lambda, you will get waves that are out of phase. Waves that are out of phase will give you destructive interference. Okay, will give you destructive interference. So that is, it starts earlier by pi, so it's a positive pi. If it starts later by pi, it's a negative pi. Sama juga, depan ke belakang ke, asalkan perbezaan dia pi ataupun half a lambda, destructive interference will happen. Because why? This is what happens. Peak with the throw with the peak, so they cancel out with each other. What is left? Nothing. It's zero displacement or zero amplitude lah. Okay. So when you have a phase difference of plus minus pi or a path difference of plus minus half lambda, you will get destructive interference or the waves that are out of phase. Okay. So again, tadi soalan Bell cakap, boleh ke is a multiple of the lambda or the phase, right? Yes, sama juga, boleh juga. So here you can see that this is pi 3, 5. So this is 1, 3, 5. So it's an odd multiple, odd integer. Tadi integer je. This is an odd integer multiple of pi. Okay, odd integer multiple of pi will give you a phase difference that gives you waves that are out of phase. And for the path difference, this is odd half integer multiple of lambda. Okay, so if this is odd integer, this is odd half. Excuse me. Let's take a look at this guy again. This is integer multiple of 2 pi. Tadi, saya cakap odd integer multiple of pi. So if I want to make this macam definition sama, remember the phase difference should be 2 pi for constructive, right? I can say it's an even integer. So for that guy, I can say it's an even integer multiple of pi. So I can change this even integer multiple of pi. So sama je. I can say it's an integer multiple of 2 pi, or I can say it's an even integer multiple of pi. So you just only need to memorize one definition. So it's either even or it's odd. Integer multiple of pi. This guy is odd half integer multiple of lambda. And the other one was integer multiple of lambda for constructive. This is for destructive. Kenapa saya cerita benda ni? Because sometimes it tells you in the question and you don't know what it means. So this is what it means. Kalau this is the expression, it means like that. It can be described like this. And if this is the expression, it's an odd half integer multiple of lambda. So that's very important to understand. Excuse me. Okay, so let's take a look at a video. I stop sharing. Am I still on record? Oh yes, I am. Let's watch this video. Let me share. Share screen. Where's the video? Kejap, nanti korang bagi tahu saya dengar ke tak dia punya video Oh, kuatnya. Sekejap. Separuh je dulu. Dengar tak?
Tak.
Oh, tak dengar. Okay, saya stop sharing dulu. Share this, share computer sound. Okay. Dengarkan sekarang.
What is light?
What is light? What is light? That's a good question, isn't it? What is light?
Isn't it an element?
Light is brightness, I guess.
We have auras,
We all have auras.
which are light.
Yes, they are.
It lights up the room. It makes it not dark.
What's the difference between blue light and red light?
The colour.
It goes in your eyes and then you see stuff.
They range from white to red to orange to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, right,
Yeah.
it would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles, or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment I've recreated today, Thomas Young's double slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803.
I brought into the sunbeam a slip of a card, about 1/30th of an inch in breadth, and observed its shadow, either on the wall or on other cards held at different distances. Besides the fringes of colors on each side of the shadow itself was divided by similar parallel fringes of smaller dimensions. Wow.
This is an experiment so simple that you could make it at home, and yet so fiddly that I have never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box.
And you can take it out on the street.
Taking it out on the street.
Could I possibly interview you guys for about a minute? We're doing a science experiment. I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm gonna place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we gonna see on the bottom
Well,
of
the
the
obvious
box?
thing you think you're going to see is you're going to see two lines.
Two lines on the bottom of the box. Two bright bands.
Two little lines.
I think,
Yeah. I think it'll be one line instead of two.
I could expect to see the whole box lit up.
It'll probably be a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, different colours.
There, have a look. You expected to see kind of one line. Is that what you see?
No.
I see dots.
How many?
It's one circle.
Well, there's one in the middle strongest, two either side.
The two on the outside are multicolored, and the one in the middle is just white.
And kind of a rainbow.
The rainbow of colour as well. Quite a few colours and lots of little dots.
Like there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that.
Okay, I'm going to stop right there. So here you can see that there are bright fringes, but it's multicolored. So the green, the red, the blue, and it's spread out, right?
That way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
Two slits.
two slits. That's incredible.
But all we're doing is we're putting a light through two very narrow slits side by side. So how does this make any sense?
There's some kind of principle involved there that the average person is not familiar with. That's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But
So this guy is moving the ball on the water to create ripples of waves. So that is waves lah. Nanti kita akan tengok light pun macam ni juga.
If I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave...
Okay, so the part where you see the peaks and the trough are where the constructive interference happens. And then the other side, you can see that it's basically zero. There's no, dia tak tinggi, dia tak turun. So it's a zero displacement there. So that is where destructive interference
meets up
happens.
with the trough from the other. Then we get destructive interference, and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up, peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there. It's light cancelling itself out.
It's basically the same as like having 2 drops of water fall in a swimming pool.
That's
You
right.
get exactly the same
And then
pattern.
they go and overlap. As this ripple overlaps with those ripples,
Yeah.
down the bottom, you get a series of, you get like a bright spot, and then a dark spot, and then a bright spot, and then a dark spot, then a bright spot. Now there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what caused the rainbowing effects as we go further from the central maximum. You saw the ones to the right were slightly colored.
Yeah,
that's
it's starting to go
because
burgundy.
the reds are going to meet up at different places than the blues.
And that's all that makes the colour differences, is different wavelengths.
Exactly.
That's amazing.
So the difference
So,
between
there's
red
so
and blue...
that red bin over there and the green part is just, I'm seeing
It's a
that and it's
different-
just different
different length.
wavelengths. And that's how we bring in all these beautiful colours all around us.
Exactly.
That's amazing. I'm amazed. Oh, good on you, thanks, Vic.
Okay, habis. So that was cool. I like this guy. He's Veritasium. This is his channel. And I watch his videos from time to time. Okay, stop sharing. Veritasium. I'm gonna share.
Doctor, can I ask?
Yep.
But this is not really important to our syllabus, but it's actually like towards like generally in science. When the people were interviewing the public and asking them the concept of light and stuff, were their opinions, were their answers valid to the concept, or they're just like simply a hypothesis? Faham tak?
You're asking me whether the people punya answer tu, yang the people that got interviewed, the answer is if it's valid or not?
Is it valid? Macam when we do surveys like that, can we straight up take those answers as samples, ataupun macam we just leave them macam tu je sebab science dah memang terbukti dengan facts.
Oh, okay. So basically what they said was hypothesis. So hypothesis can be correct or it can be wrong. So when we do experiments and we see the result, the outcome, right? So we can say, oh, the hypothesis is proven, which means that it's correct, or the hypothesis is wrong. So a hypothesis that is wrong happens all the time. It happens in my work, in everyone's work. So sometimes it works out, sometimes our theory works out. So sometimes the hypothesis does not work out. So what they said was what they think will happen, but sometimes it does not happen that way. So that is a hypothesis. So you can say that the hypothesis of the public says that blah, blah, blah. But in our experiment, we found out that actually, so that is where you come with the facts. Faham tak?
So unless the hypothesis is accepted, everything that we listen is actually a hypothesis.
Yeah.
Unless it's proven.
Unless it's proven, correct.
Oh, all right.
Mm-hmm.
Thank you, doctor.
All right, you're welcome. Okay, so tadi.
Doctor?
Yep.
Sorry to interrupt, doctor. About like our lab methodology, right?
Mm-hmm.
Like doctor, as a professional researcher, after you hypothesize something and conducted the experiment, and let's say the hypothesis is wrong, then you come up with another hypothesis and redo the experiment again.
Yes,
and again
or
and again.
I don't come up my hypothesis blindly. I read up from the work from other people. Faham tak? So I compile all these facts and I said, okay, if I change this slightly, maybe this will happen. But I don't say blindly. From a lot of reading, I come up with a hypothesis. So hypothesis is an insightful guess. It's an educated guess. You can say that. It's an educated guess. I make this guess from the knowledge that I acquired from somewhere else. So that's the best hypothesis you can have. So if someone who's not in science makes a hypothesis in science, would you believe that person? Of course not, because it's not an educated guess. Hypothesis should be educated guesses. Okay, so that's a good hypothesis. Does that make sense?
Thank you, Doctor.
Was that okay? Did you guys understand?
Yeah, you answered the question. Thank you, Doctor.
All right. Okay, so let's continue. So tadi, Veritasium, nama dia susah sebut, said that he demonstrated Young's double slit. Okay, so Young's double slit. Young's double slit. So what he did was he shined sunlight into this double slit, and what happens was there was a screen over here. Alamak, susahnya. Okay, let's do it over here lah. Padam sikit. So he had a screen which was a box basically, and it formed bright fringes, right? So these bright fringes is formed by interference. These bright fringes are formed from interference, which we saw happening with the water waves. Okay, so what happens is if light behaves as a particle, like if kita campak particle dalam slit, dalam lubang, if we campak bola dalam lubang, right? If waves behaves like particles, I would simply throw in balls into the opening. The ball would land exactly there. Betul tak? And it won't go anywhere else because that's the opening, that is where my ball would go. But what we saw was a fringe that extended beyond the opening. The fringe was spread out, right? It wasn't exactly at the slit opening, it was spread out. So for that to happen, that the light has to behave like a wave. It shouldn't be like a particle. So for waves, when it enters an opening, it goes like this, just like the water wave. And the source over here. So it looks like the ball on the water just now, kan? And here we can say that the wavefronts is where, so if I'm drawing a wavefront like this, it's basically me saying, it's basically me saying, this is my peak, this is my trough, this is my peak, this is my trough, and so on. So this corresponds to my peak, this corresponds to my trough, this corresponds to my peak, and this is my trough, and this is my peak. So when I have a bunch of waves overlapping each other, I get constructive interference or destructive interference. And when that happens, it looks like this. This is what happens. For constructive interference, bright fringes happens. For destructive, the light cancels out, just like the guy said, and there's no light there. So it's just no light, empty or dark, no amplitude. Okay, so this is when constructive interference happens. This is when destructive interference happens. So light waves, even though they have the duality in nature, it can behave like a particle, it can behave like a wave. In this case, it behaves like a wave, right? So it's almost like the water wave. They overlap with each other and they construct, the interference is constructive or either destructive. If it's constructive, it forms the bright fringe. If it's destructive, it forms the dark area. Okay, so tadi he demonstrated with sunlight and he said that the different wavelengths will give a different diffraction. Okay, so to make things simpler, we will assume first kita will assume that this is a laser of a single wavelength. We only have one wavelength. This guy is monochromatic. Okay, I pass it through a single slit. Why do I do this? Because I want this single slit ensures that my waves are in phase. What does it mean? It means that all my waves start at the same time. Betul tak? So it starts at the same time. So that's great. Now I have my wave that is first monochromatic. Second, it is in phase, or it maintains a constant wave phase with each other. So that's the condition. First, it was monochromatic or single wavelength. Second, we pass it through the slit to make it maintain a constant phase or have a same phase. Okay, so now when I have a monochromatic light which has a same phase and I shine it through a double slit, this is called a double slit. One slit is one slit, two slit is double slit. So slit is opening. So when I shine this light source that pass through this single slit and I pass it through a double slit, I will get the interference of two light waves of same frequency and phase. Okay, abaikan tulisan buruk ni, but that is what I'm trying to say. Interference of two light waves of same frequency and phase. So that is how you get your interference pattern. Okay, so they construct, dapat bright fringe, they destruct, dapat dark fringe. Okay, so that was a basic introduction on that. Okay, this one. Okay, dah tahu dah ini. This one pun kita dah cakap in detail. Constructive interference, destructive interference. Okay. So now we know that we have waves that interferes with each other either constructively or destructively. How do I make sense of where the bright fringes are? How do I know where the position of the bright fringes are or where the dark fringes are? So there's a way to calculate for this. Of course, everything. Mesti ada calculation. Okay, so we start with this guy first. So this is my first opening, this is my second opening. The distance between these two slits is called D. Okay, that's a D. And the distance between my slits and the screen is called L. Okay. The point that they interfere, in this case, this wave number 1 interferes with wave number 2. This is called Y. Okay, Y can be 0, Y can be positive, Y can be negative. Above the central point, it is a positive. Below the central point, it is a negative. Sama je macam axis biasa. So Y, what is Y? Y is the, kenapa macam tebal gila ni? Y is the position of the bright fringe. So dia akan bagi tahu kita, if Y is 10, oh, that is the position of the bright fringe. If Y is 5, that is the position of the bright fringe. So Y tells us the position of a certain fringe. It can be either bright or dark, but we will talk about the bright one first. Okay, so bear with me. So kita dah cakap pasal D. D is the distance between the two slits. L is the distance between the slits to the screen. So that's L. And Y is the other axis that shows us the position of the fringes. Okay. In this case, sorry, not in this case. Before this, we have talked about for constructive interference to happen, our wave phase difference should be, sorry, our path difference should be, berapa tadi? 1 lambda, right? 1 lambda. And for destructive, our path difference should be half a lambda. Okay, so if this guy is a bright spot, it means that they are interfering constructively. Betul tak? So here I have the path of the wavelength, sorry, the path of light number 1 and the path of light number 2. What is the phase? What is the path difference? Susah ni nak tukar-tukar. What is delta L in this case? The answer is 0. Sebab they come from, basically they are meeting at the center point. They have the same equal distance. So L is equal. So at that point, your path difference is 0. So that's good. Next case, what if we form a bright area over here? So here we have path number 1, L1, and path L number 2. So here we can say, oh, the difference in the path of L1 and L2 is delta L over here. What should be the difference? What should be the path difference between these two waves for a constructive interference to happen over here? It should be m times lambda, or m 2 pi, multiple of 2 pi. So that was the condition for constructive interference to happen. Okay, so bear with me, saya nak derive ni. Any questions so far? Yep.
Can doctor please repeat again how to get the phase difference and for the first figure and the second figure, because I'm not understand about it.
How to get the path difference of the first figure? This figure?
Yes.
Oh.
Why?
Sebab dia symmetrical meson. Meson kan? Dia symmetrical.
Yes.
And sini pun symmetrical. The distance between here and here is the same. Sebab ni center point. So if I start from here to the center point, I start from here to the center point, the length should be the same. Does that make sense? Macam nak cerita? Macam nak cerita? Okay, let's draw a triangle. So if I have a triangle that looks like this, okay, the sides are the same. This guy is 10 and this guy is 10. So what is the length of this guy and this guy? Does anyone know? Should it be the same? For an, is it isosceles triangle, I think? If this is 35. If this is 3 and this is 10, this is also 3 and this is also 10 by symmetry. Faham tak? Faham tak, Mizan? So this is the center point. So I'm trying to say that this is just a triangle, and by symmetry, this is L1 and this is L2. So the lengths are the same. If the lengths are the same, the path difference is 0. Remember, delta is the difference. Okay, so this is L1 minus L2. If L1 is equal to L2, so it's 0. Is that okay?
Yes.
Okay.
So why path difference is important at here?
So why is path difference important? Okay. Because sometimes, because our light does not only interfere at the center, our light interferes at multiple points. Remember, it spreads out indefinitely wide. So when that happens, kita nak tahu what is going on over here. So we need to know what is the path difference. And the path difference will tell us what is the position of the bright fringe. Kita tak nak tahu tengah-tengah je, kita nak tahu bright fringe kat sini kat mana, bright fringe kat bawah ni kat mana. We want to know where those bright fringes are. So that is why defining the path length is important. Here the path length is 0. That's great because the length is the same. What if the length is not the same? We have a path difference. For a constructive interference to happen or for a bright fringe to happen, the path difference must be a multiple of lambda. Multiple of lambda or m lambda. Or a multiple of 2 pi phase difference. But kita nak cakap pasal path length je, so kita cakap pasal m lambda je. Okay, so that's just lambda. It should be a difference of lambda sahaja. It can be 2 lambda, it can be 3 lambda, it can be lambda, it can be 4 lambda, asalkan multiple of lambda for bright fringe to happen. And that's not the only place that we are concerned. Because of course, kita ada bright fringe over here, bright fringe over here, bright fringe over here, bright fringe over here, bright fringe over here. What if I want to know where is the position of this guy? So this guy, constructive interference over here, what is the path length? So I need to know those things. So I want to approximate I want to approximate this diagram for me to get an equation. Okay, where is that figure? A figure that lets me, okay, it's this guy. Okay, so tadi we talked about this guy having the same path length, right? So it was a 0. It was a 0. The delta L was a 0 for here. Okay, so that's easy. That's the easy part. What if we will have a bright fringe over here? So here I draw out my wave length, and the wave from this guy over here, the path difference is this much. I mark it as delta L. Okay, so bear with me, saya nak derive ni. So that the path difference between the first length and the second length is delta L. So this is theta. If this is theta, I can also say this guy as theta. Why? Because this is for this, a triangle has 180 degrees, right? Triangle has 180 degrees. So if this is theta and this is 90, so the other angle should be the other angle should be 90 minus theta for this to be equal to 180. So now I know that this guy is 90 and this guy is 90 minus theta. So it adds up. Theta plus 90 minus theta plus 90 gives me 180. So it's complete. So if this is 90 minus theta, what is this? This is 90. 90 minus 90 minus theta is just theta. So this guy is theta. If this is theta, this is also theta. Okay, you don't have to know this. I'm just showing this for you for the derivation purposes. So jangan panic. Okay, so that if that is theta, then this guy is also theta. Part 2 je yang kena faham sekarang ni. Okay, so now that I know that this is delta L and this is L and this is my theta, so I can say that sine theta is equal to opposite over hypotenuse. What is my opposite? Opposite is delta L. My hypotenuse is this guy, D. So I have my first equation. Sine theta equals to delta L over D. Okay, so itu by geometry je. Jangan pening-pening kepala. Just remember that it's by geometry. I define sine theta equals to theta L over D. It's opposite over hypotenuse. This is the path difference between the two waves. Okay. All right. So next one. Now I want to relate it to this theta. So this theta, opposite, I have the distance y. Sometimes I don't. Sometimes I do have the distance y. So this is y over L. L is always given. Sometimes it's not given. So it depends. So tangent theta is equal to y over L. It's opposite over adjacent. So what is opposite? Opposite is y, adjacent is L. So tangent theta is y over L. That is my second equation. Okay, bear with me, sabar dulu. Now, in the Young's double slit experiment, the D was very, very large compared to delta L. Of course, the path length is always super small, always very small. Okay, so when it is very small and when L is greater, much greater than Y, the distance between the slit and the screen is much greater than the fringes, then we can say that theta is very, very small. Maksudnya theta ni kecil lah sebab kita punya L ni sangat-sangat besar compared to Y. So this is Y. So this is very small theta. Betul tak? As L is lagi panjang L compared to Y, lagi kecil theta tu. So with this in mind, when D is much greater than delta L and L is much greater than Y, we can say that theta approaches 0 ataupun theta is very, very small. When theta approaches 0 or is very, very small, we can say that sine theta is equal to tangent theta. Okay, to prove this, let's use our calculator. Sine 0.001 is equal to tangent 0.001. Okay, so I'm going to use my calculator now to prove this. Sine 001 is equal to 1.74 times 10 to the minus 5. Tangent of 0.001 is 1.74 times 10 to the minus 5. It's the same thing. So here, tak tahu lah macam mana, but math. So when the angle is super small or approaches 0, sine theta is equal to tangent theta. Now remember, we had two equations from before that we derived by geometry. So we can equate these two things together because sine theta is equal to tangent theta. So now I will get this equation. Where should I draw it? But where should I write it? I'm gonna write it here. So sine theta tadi was d, oops, sorry, it wasn't d. It was delta L over d, opposite over hypotenuse. Tangent theta was opposite, which was y, and L over L. Betul tak? Okay, betul. Opposite over adjacent, y over L. So now I can equate these two things together. Delta L over D is equal to y over L. Now remember, for constructive interference to happen, delta L should be equal to a multiple of lambda. A multiple of lambda. So if I were to substitute that, I would say multiple of lambda in my delta L, T, this is for bright fringe over L. So my equation for bright fringe is just ML lambda over D. So what was the assumption that I used to get this equation? My assumption was that theta is very small. Kalau theta tak cukup small, if theta is big, I cannot say sine is equal to tangent theta. So this equation does not hold. This equation only holds if my theta is small or approaches 0. Okay? Any questions so far? Nanti nak masuk dark pula. Is everyone okay so far? It's quite heavy, right? Okay, I'm gonna continue.
Doctor, can you give 30 seconds to for us to take this down? Thank you.
All right, sure. Wow, banyaknya nota daripada pensyarah lain. Nanti saya forward kat korang. Yay, bagus. Okay. Is everyone okay? Okay, everyone. Everyone is on the same page as me. Any questions that is bugging your mind? No questions. All right. Moving on. So just now we talked about the bright fringe. So this is bright fringes or constructive interference. What did we assume? Theta is very, very small and the path difference must be a multiple of lambda, which is how we got this guy. Multiple of lambda for constructive interference to happen. So this equation describes the position of bright fringes. Okay, now let's take a look at this diagram. So we know what D is, we know what L is. Let's make this bigger. And if I were to say M is the order number. Saya lupa cerita. M is order number. So that is order number. Let's say I'm asking you what is the central bright fringe. Central bright fringe. The central bright fringe happens at 0. Happens at M equals to 0. So how do I use this equation? Y 0 equals to 0. So it's just 0. It happens at 0. Betul lah, sebab kat center kan. So it's at 0 position. That was easy. What about 1? If I want to find out what is the first order of bright fringe. The first order bright fringe. So Y1. So that is at M equals to 1. So Y1. 1 lambda L over D. Okay, so if you know what D is, you know what L is, you know what your lambda is, you can find out the position of this guy from the central point, from zero, x-axis lah. So if my answer is 0.1 centimeter, it is 0.1 centimeter from the zero axis, from the 0th order brightness. If that is a positive. If my answer is a negative 0.1 centimeter, it is down here. I am talking about this guy over here, negative 0.1 centimeter. Okay. All right, so that is for bright fringe. Now, we talked about constructive interference happening when it is the difference, the path difference is 1 lambda. And destructive interference happens when the difference, when the path difference is half a lambda. So how do I make this equation half a lambda? So, senang je, tambah 1/2. So, the same equation, but tambah 1/2. M plus 1/2 times lambda L over D. So, nak derive ke? Tak payahlah. Korang hafal je lah So, it's going to take some time to derive that. But it's basically the same thing. If the two waves construct, the path difference must be equal to half a lambda, multiple of half lambda. So, derive sama je macam tadi. So, sine theta equals to tangent theta. It's the same thing, exact same thing. Except that we have this 1/2. Okay, something that I want to emphasize on. During your test, a lot of you guys said 1/2 mv squared 1 minus 1/2 mu squared is equal to 1/2 mv minus u squared. Salah, this is not the same. How should it be? 1/2 mv squared minus u squared. Beza Kalau v minus u squared, it's actually v squared minus 2uv plus u squared. So it's different, it's totally different. Okay, so this is a math error. I know you understand what the equation wants, but this is error on the math. So I want to emphasize to you that this bracket is very, very important. If you leave it out, it just means that the 1/2 times lambda times L. If you have this bracket, it means M plus 1/2 times with lambda times L. So the bracket is very important. Okay, so please take note, math kena cemerlang jugalah nak buat fizik ni. Basic math, it's not even integration. Okay. Okay, so again, this is bright. This is for dark. What is dark? It happens for destructive interference. Bright is for constructive interference. Okay, and the order number starts from 0. So why 0 kat sini? Just 0, bright fringe. Why 0 for this guy is 1/2 lambda L over D. So it works out for both. So M starts from 0, plus minus 1, plus minus 2, so on. It's an integer. Okay. All right. Any questions before we start our example? Hopefully boleh siap sempat. Yep. Yeah.
So for the double slit just now, we just remember what is the formula for black fringe and dark fringe, right?
Yes, correct. Okay. A Young's double slit has a... Oh yes, ada soalan lagi?
Doktor.
Aha.
Can I know apa yang Imagine tanya? Sebab saya tak dengar. Tiba-tiba doktor kata yes.
Mazen tanya, kita kena hafal equation bright fringe dengan dark fringe je ke untuk double slit? Jawapannya ya. Tu equation yang kena hafal. Dengar ke?
Dengar. Thank you.
Okay. I kan terputus tadi. Alright. So let's do this example. A Young's double slit has a slit separation. Slit separation is D. So that is D equals to 2.5 times 10 to the minus 5 meter on which a monochromatic light beam is directed. So this is a single lambda. The resultant bright fringes on a screen 1 meter from the double slit. So this is your L, right? 1 meter. So this is D, your slit over here. Okay, and then this is your L. This is your screen. So that's your L. This is your D. Are separated by 2.3 times 10 to the minus 2. Dia cakap resultant bright fringes are separated. So if I have a bright fringe over here and a bright fringe over here, kat sini dark, bright fringe over here, the distance between these two guys is 2.3 times 10 to the minus 2. That is what it is saying. The distance between the two bright fringes is 2.3 times 10 to the minus 2. Now, my question is, does it matter which bright fringe I'm talking about? The answer is it doesn't matter. Kenapa? Sebab for a double slit interference, the fringes are always equal in distance. The intensity might not be equal, but the distance is the same. If from the second order to the first order is 2 centimeter, then from the first order to the 0th order is also 2 centimeter. Also 2 centimeter, also 2 centimeter. So it's the same at every point. So it doesn't matter which bright fringe I'm comparing. Between the distance between two consecutive bright fringes is the same everywhere. Okay, so how do I generalize this? Ym plus 1 minus ym is equal to the same at everywhere. So whatever the value is lah. Ta-da, I don't know. So if I were to say m equals to 0, it's 1, y1 minus y0, sama. If I were to say m is equal to 2, so that is y3 minus y2. Sama je, distance dia akan sama. So I can generalize it like this. Okay, so that's something I need to point that out. But you don't have to memorize this. You can just look at this diagram and remember that they have equal bright fringes. So, tak payah hafal pun sebenarnya. Okay, so moving on to this question balik. Okay, I hope that was clear. Kalau ada soalan, please just ask me, okay? What is the wavelength of this beam? So I don't know what my wavelength is, but thank God it's only a single wavelength. So what is the equation? We are talking about bright fringes. So my equation should be y equals to m L lambda over t. So what is my m? What am I trying to find? I have this information. I have this. I have the separation equals to 2.3 times 10 to the minus 2. So what shall I solve? If I were to say my m is equal to 0, then this guy would be y1 minus y0 equals to 2.3 times 10 to the minus 2. We know that y0 is just 0, right? Because if I plug in 0 over here, my y just becomes 0. So I can say that my y1 is equal to 2.3 times 10 to the minus 2. Now, if this is y1, I want to make this guy y1 as well. So this is 2.3 times 10 to the minus 2 equals to 1. M is equal to 1. L is equal to 1. Lambda is, I don't know. I'm trying to find that out. D is 2.5 times 10 to the minus 5. So now I can solve for lambda because this whole guy equals to 2.3 times 10 to the minus 2. So lambda is, I don't know, kejap, check balik. Lambda is, from my calculations, 575 nanometer. Ataupun 5.75 times 10 to the minus 7 meter. Betul. Okay, so you can either write your answer in nanometer or in scientific notation. Doesn't matter, same thing, same answer. Okay, so the answer is that. So here, what did we use to answer this question? We first said we first used the equation for bright fringe. It's different than dark fringe, so you need to know that. So the equation for bright fringe is just m. For dark fringe is m plus 1 over 2 dalam kurungan. And then we had to use this guy. The difference between two bright fringes is 2.3 times 10 to the minus 2. Okay, So that was the two equations that we needed to find out what is lambda. Right, moving on. Next one. Sorry tak ada break hari ni. Kalau rasa penat, saya kasih 5 minit je. Nak stop dulu ke? Do you guys want a break? You guys okay? I'm going to continue.
Okay.
Okay, nak cepat kan? Okay, so two narrow slits are 0.025 millimeter apart. So that is your D. Two slits, that is your D. Okay. Millimeter, so times 10 to the minus 3 meter. Okay, when a laser shines on them, so laser selalunya single wavelength. Bright fringes form on a screen that is a meter away. So your screen is 1 meter away from the slit. So that is your L. Kenapa? Tak ada apa-apa? Okay. So these fringes are 3 centimeter apart. So dia cakap from one bright fringe to another bright fringe, the separation is 3 times 10 to the minus 2 ataupun 3 centimeter. So what is that? What is the separation between the second order bright fringe and the central fringe? Central fringe is Y0, second order is Y2. Now we already know that Y0 is 0 because M is equal to 0, ML lambda over D. M is 0, so everything is just 0. So that is easy. I want to know what is Y2. So how do I find Y2? We have this information, so we can find out what is Y1. So Ym plus 1 minus Ym is equal to this guy or this guy. Okay, so if I start my M with a 0, it's going to make my life easy. So if this guy becomes 0, this guy becomes Y1. Y1 is equal to 3 times 10 to the minus 2. Okay. I want to know what is my lambda for me to find out what is Y2. So this is equal to ML lambda over D. Ada soalan ke? One. Don't know what lambda is. D is 0.025 times 10 to the minus 3. Equal to 10 times 10 to the minus 2. So now I can solve for lambda. Lambda is 7.5 times 10 to the minus 7. Okay, so that is lambda. Now I can find out what is Y2, which is just ML lambda over D. So M is just 2, L is 1, lambda is 7.5 times 10 to the minus 7, and D is the same thing as that, 0.025 times 10 to the minus 3. That will give me, entah berapa? Y2, tak kira pula Y2. Oh, it's 0.06 meter. Okay, so the question is asking what is the separation between the second order bright fringe and the central fringe? So Y2 minus Y0 is just Y2, so this is your answer. Now, we had a clue just now. It was these fringes are 3 centimeter apart. And here we found out that Y2 is 6 centimeter. Now let's take a look at the diagram again. I told you if one of them has a distance of 3, the rest of them will have a distance of 3 as well. So if this guy to this guy, the 0 to the first, sorry, the question said apa tadi? The distance between random fringes. These fringes are 3 centimeter apart. So cakap random lah. So if this guy is 3 centimeter apart, this guy should also be 3 centimeter apart. So the question asks you, what is the distance between Y2 to Y0? So it's just 6. So that's a shortcut. Boleh juga. Okay, so but using the equation, of course, is more accurate. Well, tak tahulah, kalau salah kira, salah juga. So that is how you can check back on your answer lah, okay? So this is me telling you this method so that you can make sense of things It should be intuitive. If your bright fringes are 3 centimeter apart, it is 3 centimeter apart everywhere. So basically, it's just an addition of the distances. Okay. All right. Next example, a light source simultaneously emits light of 2 wavelengths. Okay, so this is going to be a little bit difficult than the usual one. So we have 2 wavelengths, 480 nanometer and 560. So the first lambda is 480 nanometer and the second lambda is 560 nanometer. The source is used in a double slit interference experiment. Okay. Okay, so how does this look like? So kita ada laser. Laser ni sebenarnya light tak adalah campur macam tu je. Dia akan ada 2 warna. Akan ada separation tengah-tengah ni. So satu ni 480, satu ni ada 560. So when you look at the light, there's 2 colors. And these colors come from the same source, so they are shined like that. Okay, so that is how it is. So when these 2 wavelengths are shined on the double slit, of course, diffraction happens and they interference happens either constructively or destructively, and of course the fringes happens as well. But our equation y equals to ml lambda over d only has 1 lambda. So how do we find out for a source that has 2 lambdas? Does anyone have any idea? How do we find out the y for 2 different lambdas? Saya tak tengok soalan lagi I'm just asking you in general. Remember the YouTube video that we saw. So we could see a multicolor fringes. Why was that possible? No one has any idea? Okay, so I'm going to give you the answer lah. So if you have a different lambda, you will have a different y. That is why when in the YouTube video, we saw this guy was white and then we had green over here. We had, we had red and then we had green and then we had blue. So they did not overlap with each other because why? They have different wavelengths, which means that they have different y. If they have a different y, their bright fringes form at different places. Okay, so we can use this same equation, but the lambda must be replaced lah. Okay, so how do we do that? So let's take a look at this question first before we start. So a light source simultaneously emits 2 light wavelengths, okay? The source is used in a double slit interference experiment where the slit spacing is T is 0.04 times 10 to the minus 3 meter. And the between double slits and this and the between the double slits and the screen is 1.2. Okay, that's pretty straightforward. Alamak, saya terpadam lambda 1 dengan lambda 2. 480 nanometer and 560. Okay. What is the separation between the second order bright fringes? So tanya, what is the separation between the second order bright fringes of the 2 wavelengths? Dia nak tahu what is y2 for lambda 1, what is y2 for lambda 2. Whoa, what was that? Lambda 2 and this is lambda 1. Macam mana saya nak buat ni? Notation. Saya tak nak buat macam tu. So this is for lambda 1. Kita buat kecil. Lambda 2. And what is the difference between them? So this is the question. So I think you can already guess by now. We just find out what is m equals to 2, find out what is the y, and then tolak je lah. Okay, so y for the first lambda. So y2 for the first lambda is ml lambda over d. M is equal to 2 because that is what we want to find out. L is 1.2 and lambda is 480 times 10 to the minus 9. Nano is minus 9. Micro is minus 6. Tolong jangan keliru. Okay. So with that, divided by D is 0.04 times 10 to the minus 3. So my answer is, this is 12.3. 28.8 times 10 to the minus 3 meter. Okay, so next one, y2 of lambda 2 is 2, 1.2, and the second wavelength, 560 times 10 to the minus 9, divided by D. Okay, so the answer is 33.6 times 10 to the minus 3. Kalau saya salah kira, bagi tahu so the difference between these two y's, right, is y2 lambda 1. Oh, lambda 2 lagi besar. Lambda 2 minus y2 lambda 1 is equal to 4.8 times 10 to the minus 3 meter, or 4.8 millimeter. Okay, so the difference between the second order bright fringes of wavelength 480 nanometer and with Y2, second order bright fringe of 560 nanometer wavelength is 4.8 millimeter. Now, what does that mean? What is this separation? If I were you, I would just say, oh, benda doktor cakap ni, tak faham weh, macam tu kan. Because that is how I behaved in high school. Okay, so how does that look like sebenarnya? Let's talk about it. Okay, please bear with me. I know it's heavy stuff, but it's very important. So, tadi kita cakap pasal 480 nanometer versus 560 nanometer. Now, I have to tell you, 480 is actually blue light. Kalau tak tahulah. I'm just telling you, this is just general info. You don't have to memorize. So 560 is green light. Now, remember in the YouTube video, we saw that the blue did not overlap with the green did not overlap with the red, and so on, because they have different wavelengths, which means that they have different y's. Why is that? Y equals to m L lambda over D. Now remember, L, D are the same, they won't change. The only thing that would change is lambda, because our wavelength is different. If my lambda increases, my Y also increases. Again, if my lambda increases, if I use a green wavelength, I will have a larger Y. So let's say my Y for green one is over here. So that is when my lambda is greater. The light intersects and constructive interference happens over here. What if my lambda was smaller? My Y would also go down. Because this is just the equation. If my lambda is going down, my Y also becomes smaller. So I would say my my blue would intersect somewhere here. How do I do this? So the Y is much smaller. This is the Y. The Y from the central point is much smaller than the Y of the green from the central point. So my blue would interfere constructively over here. Okay, and then what about red? Red has a wavelength of berapa? 600 ke? Tak ingat. Pantai je lah, 600 lah. So red. So red is greater than green, much greater than blue. So if my lambda is much greater, my Y should also be much greater. So they would meet up somewhere up here. This is where the constructive interference for red would happen, because red has higher wavelength, it has a longer wavelength, which means that the Y is also bigger. What is Y bigger? It means that the distance from the center point to the position of the bright fringe is greater. Okay, ouch, it's greater. So the Y depends on the wavelength. So if I were to say the second order of the green with the second order of the blue, let's say the green intersects over here, but that's a blue. Let's say the blue intersects over there and the green intersects, they interfere constructively over there. and this is the second order. The distance between these two guys is what our answer is 4.8 millimeter. So the difference, the distance between the bright fringes is 4.8 millimeter. I hope that makes sense. Okay, so moving on. Any questions so far? I know it's pretty heavy and we just learned about it, tapi kena laju sikit. So, but if you have any questions, feel free to ask. Yeah? It doesn't matter if you think it's stupid or a basic. Tak apa, tanya je. Yes, Belle.
Doctor, why is the light intensity, or like why is the fringe brightest at the middle and then it wanes as we go to the side?
How do I explain that one?
Is it really out of our syllabus that we shouldn't ganggu it yet?
For double slit, yes, it's not part of the syllabus. Tapi kalau single slit nanti kita cakap pasal intensity. Is that okay?
Okay, doctor. So I'll wait for the single slit then.
Alright. Tapi betul, what Belle said was correct. As it goes further away from the center point, the intensity becomes dimmer ataupun lower. It's just, there's an explanation for that, but I don't have it in mind. Okay, so sorry for that. Okay, so continuing with single slit diffraction. Diffraction is the slight bending of wave as it passes around the edge of an object. So we know that we have wave fronts. Remember, we had the ball on the water, and he did that, and waves was formed. So it made wave fronts, right? If this wave fronts met with a barricade, macam ada obstacle lah, and there is an opening over here. This is a blockage, and this is an opening. The wavefront would behave like this. Okay, this is called diffraction. Okay, I think I've said this in Young's double slit as well. So the bending of light or the spreading of light is called diffraction. Okay, it happens when light meets an obstacle and there is a small opening. So the light goes out from that opening and diffraction happens. Diffraction is the spreading of light. Spreading or bending of light. Okay, so it can happen if there's an opening, or it can happen when there is a sharp edge. Macam ni, there's an edge. Bukan sharp edge, there's an edge. So this is an edge. Tak nampak lah pula. There is an edge. Let's say this edge is warna hitam. Batu lah, batu. This is a batu and water is moving and then, oh, dia terlanggar batu. So what happens? It bends. So that is diffraction as well. Walaupun it's not an opening, it's just an edge. Faham tak? Okay, so that if it meets an edge or it meets an opening, diffraction happens. This is when you have an opening. Diffraction happens. Okay, so the point of this is to say that diffraction happens when waves meet with edges or openings. Diffraction happens. In terms of wave propagation, this is explained by Huygens principle. Any point of the wave front can become a source of a new wave. We will talk more on this. Diffraction occurs with all waves, including sound waves, water waves, electromagnetic waves, such as visible light, X-rays, radio waves, and so on. So any type of wave, diffraction can happen. So sound wave, water wave, and so on. The things that we have seen, sound, we have seen water in the video, we have seen sound in previous chapter. Now we are talking about the waves that we can see, visible light. Okay, so diffraction is the slight bending of wave as it passes from around the edge of an object or through an opening. The amount of bending depends on the relative size of the wavelength to the size of the opening. Now, this is very important because the size of your opening should be comparable with your wavelength, wavelength of light. Should be comparable. Now, remember, wavelength is in meters. Your opening is also in meters. The value should be comparable if you want to see the fringes to form. If it is not comparable, for example, I open a door, right? Okay, so sekarang ni it's pitch black. outside there is light. I open the door slightly, right? It's pitch black everywhere except outside. I open the door, so the door acts as, macam saya lukis door macam ni. Teruknya door ni. Macam mana? Korang faham tak saya cerita apa ni? So this is my door. Macam tu. Okay, that's my door. This is pitch black. This is bright outside. So this is actually an opening, right? So will diffraction happen in this way? Will the diffraction of light happen? That's my question.
Yes.
Why?
Yes.
Because
Huygens commanded the wave to follow his principle, so it has to do that through the obstacle or through an
Betul, part 2 betul, but remember I told you the opening should be comparable to the wavelength of light for you to observe diffraction. So can you see diffraction? If you open your door, can you see diffraction happening? Can you see the light diffracting?
Oh, doctor, is it because the opening is bigger than the wavelength of light?
Yes, that's correct. Because when you open the door, of course, it's it's not 1 meter, I know, it's not 1 meter, but it's basically big compared to the wavelength of light. And light is very small, light is in nanometers. So when you open your door, the opening is so big compared to the wavelength of light. There is diffraction, but you can't see it. For you to see diffraction, the size of the opening should be comparable to the length of the wavelength. The size of the wavelength. Kena comparable. Contohnya, if your light is 560 nanometer, your opening should be around nanometer as well. For example, 800 nanometer is acceptable, 1000 nanometer still acceptable, but when it comes into centimeter, millimeter, it's no longer comparable. So it should be in nanometers as well. Okay, so that is how small the slit is when you do this experiment. It's comparable to the wavelength of light. Okay, so that is a fun fact for you, right? Okay, so this is a single slit diffraction. Previously, we talked about double slit. Double slit is kita ada dua diffraction and they construct with each other. They interfere with each other either constructively or destructively. Now we have a single slit, which means that it only has one opening. So the light goes like this. How do they interfere with each other to form fringes? You can't interfere with yourself, right? Boleh ke? Tak boleh kan? You can't have a fight with yourself. You can't date yourself. That's so weird. You have to have someone else for you to interfere. Betul tak? For the double slit, it was easy. It was very intuitive because we have two sources. We interfere. We could date. We could fight. Whatsoever. Here, I'm alone. I am alone. How do I interfere? How do I form the fringes if I am alone? Betul tak? Okay, so here comes the Huygens principle. Is it Huygens? I forgot. But it's a principle lah. So the principle said, I think it's Huygens. Check balik. Yeah, it's Huygens. The wavefront can become a source of a new wave. Okay. Don't panic, okay? You know, it's very alarming to read that sentence. Okay. So Huygens said, oh tak apa, walaupun sorang-sorang boleh interfere. How? I know, I hate Huygens too, but it's okay, let's learn. Okay, so Huygens said, okay, walaupun wavefront ni dia sorang-sorang dia, but the fringes can form because when we have a wavefront, okay, when we have a wavefront like this, actually a wavefront consists of many sources of light. So this point is one light, this is one source, and so on. So one wavefront is composed of an infinite amount of wave sources or light sources. Okay, please absorb that. One wavefront consists of an infinite amount of light sources. Okay, so if that's the case, right? If we have a source over here, so it would produce something like this, right? Tapi tak nampak pun. So if it's infinite amount of wave sources, they would diffract and they would interfere and we would see it, but we don't see it. So what happens? So when they interfere with each other, it becomes complicated, it becomes a mess. It actually cancels out, adds up, blah, blah, blah. The result is exactly, it looks exactly like the wavefront. I know, right? Penat je. So banyak-banyak source ni, they overlap, superposition, blah, 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 messy, complicated. Last jadi wavefront balik. It looks like a wavefront. So when this wavefront, oops, kita semangat pula. When this wavefront lalu dekat another slit, right? When this wavefront lalu dekat another slit, let's use a different color for that. When this wavefront, blah, 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 kejap. Okay, so that's in my slit. When this wavefront lalu this slit, so only this part of the source, yeah, the infinite amount of source, only that much can go through. And let's say I only have 3 that gets passed through, contohnya, but that's not the case. If I only have 3 that can pass through, now I can see the interference happening. Sebab dia smaller amount. When the smaller amount, I can see the fringes better. When it's so much, I can't see it. It just basically looks like a wavefront. But when it's filtered and only a little bit of wave sources interfere with each other, I can see the diffraction happening. But in reality, diffraction happens everywhere. But I can only see it when a small amount of wave sources interfere with each other. Okay, so I hope that makes sense to you. Okay, so when this guy, even though it's from a single wavefront, this wavefront has many sources. They interfere with each other, so they form fringes. So this fringe looks like this guy. So we have a central bright fringe at the center, bright fringe at the center, and then the intensity becomes less and less as it propagates away from the center. Okay, so this is if we have a single hole, and if it's a slit, like the Young's double slit, it would look like, mana? Sekejap, cari contoh. It would look like this. This is for a slit. Tadi tu hole. This is a slit, macam rectangular slit lah, rectangular slit. So it looks like this. A central bright fringe, and then a less intense fringe, a lesser intense bright fringe, a lesser intense bright fringe. So this guy, apa benda yang kat sini kan? What on earth is this? This is to show you the intensity of light. So it's just a graph basically. Intensity of light. So the higher the peak, the higher the intensity. So that is what it means. And this guy is intensity of light. This guy is your position of Y. Sama macam double slit tadi. Okay, so so I told you like roughly how it forms, even though it comes from a single source. Basically, it is made up of many sources based on Huygens principle. So this is called A. Tadi we had D. D was the distance between 2 slits for Young's double slit. This guy is called A. This guy is still an L. This guy is still Y. So that's great. We only have to take note of A. That is different. And this guy is not usually there. This plot of the intensity is just to show you, to give you an idea that the center has enormous intensity compared to the rest. Tu je, you don't have to plot it. Okay, so the center ni memang paling besar lah, yang paling-paling. Memang tak boleh nak compare lah, yang lain tu memang kecil gila sebenarnya. Sebenarnya lagi kecil daripada tu. So this is just to visualize it. Okay, so as you can see here.
Doctor, what is A? Is A the size of the slit?
Yes, A is the size of the slit. Sorry, so A is the size of the slit. This guy.
Thank you, Doctor.
All right. Okay, single slit diffraction pattern. Okay, so this is an actual visualization of the intensity. So as you can see, this guy is like super huge compared to the rest. The rest is like blah, right? So the center is like gila, strong, super strong intensity. So this is the actual intensity lah sebenarnya. So this guy is just, ini macam tak betul lah sebenarnya. Sebenarnya tinggi daripada biasa. Sebenarnya it looks like this. Okay. But this is for your learning purposes. So they make it bigger a bit so that you can see it. Okay. So remember, destructive interference happens when the path difference is a multiple of pi. It's an odd multiple integer. Is it? Kejap, cek balik. The path difference should be berapa tadi? Let's go back to our slide. This is not the slide. Is it this one? Destructive? For destructive interference, path difference is 1/2 lambda or pi. Odd half lambda or multiple of pi. Odd multiple of pi. What did we conclude just now? I concluded it somewhere. Right, this is odd half lambda or odd multiple of pi. Okay, I think that's right. Mana pergi dia? Kejap. Not this one. I was going to talk about this guy. Okay. So here is your bright fringe, right? This is your bright fringe. For single slit diffraction, we will derive an equation for your dark instead of your light. There's a reason why we can only derive for dark instead of bright, but we won't go into that. So for double slit, we derived for Y bright, and we got the Y dark by basically adding M plus 1/2, right? Dalam kurungan. For single slit diffraction, the general equation is for Y dark. So that is something you need to take note of. So the equation looks like this. I'm just going to show you the equation first. It's this one. Ym ml m lambda L sama ml lambda over A. Tadi it was D, right? Previously it was Y equals to m L lambda over T. Now it's m lambda L over A or m L lambda over A. The difference is in the A. This guy is for a dark fringe. Previously it was for a bright fringe. So that is something that you really need to take note of. Okay, so single slit, dark fringe. Double slit, bright fringe. Okay. Okay. So here, let's derive the equation. So here we have two waves. Remember, one wavefront is a source of multiple waves. One wavefront has multiple wave sources. So this guy constructs, sorry, doesn't. So this guy should be, kat mana yang nak tunjuk ni? How do I show it to you guys? This is not a good one. 8/2. This is not a good gambar. Okay, never mind. Let's go on with the equation first. Nanti saya akan cerita macam nak derive if you guys are interested. Recording. Okay. So the description of a single slit, it will have a broad, intense central band. Okay, this is what we can see here. The central band will be flanked by a series of narrower, less intense secondary bands called the secondary maxima. So this guy is called the central band. Okay, and these are called secondary maxima. The bright fringes, tapi yang bukan central. So it's called the secondary maxima. So both sides. The central band will also be flanked by a series of dark bands called minima. So the dark places are called minima. Okay, so secondary maxima and minima. So this guy is minima. So that's just terms that you need to know. Secondary maxima, central band, and minima. Okay, so according to Huygens principle, each portion of slit acts as a source of wave. The light from one portion of slit can interfere with light from another portion. The resultant intensity on the screen depends on the direction of theta. Sebenarnya sama, dia punya derivation is basically, remember our derivation was d sine theta equals to, it was sine theta equals to lambda L over D. Here, it's sine theta equals to lambda L over A. So the path difference is divided by A instead of D. And then we have tangent theta equals to Y over L, sama. If the angle is small enough, these two things will be equated to each other. Sekejap. This is A over 2. Kenapa A over 2? So this is A over 2, sorry. This guy is A over 2. Sebab dia start pada center. Dia bahagikan dua to get the triangle. Okay. Nantilah kita cakap pasal ni. But I just want to share with you delta L A over 2 so that you get A over 2 sin theta equals to delta L. Tangent theta is Y over L, sama macam tadi. And then we assume that the theta is close to 0 or super small so that we can equate the sin theta with the tangent theta. So now we have delta L over A over 2 equals to Y over L. I hope I'm right. Okay, so let's see how that goes. So YL, okay. Mana sign tadi? Sign. Dia tak tunjuk pula sign. Patutnya dia derive. Sign. This is not helpful diagram. Kat sini is where destructive interference happens. Sin theta is equal to lambda over A. But there's no diagram for that. Okay, tak apalah, nanti saya explain pasal ni. So the equation for your position of dark fringe is basically like this, but over A. Sama je macam double slit except it's over A and it gives you the position of the dark fringe instead of the bright fringe. The derivation, I will make it in another video. So let's talk about this example. Alah, tak sempat. So I tak sempat derive and I tak sempat do the question. So I'm going to do that in a separate video, if that's okay with you guys. I won't have class on Thursday because your quiz is due on Friday. So what I will do is I'm going to make the video after this class. I'm going to share it with you guys and you can watch it at your own time so that you can answer your quiz. Is that okay with everyone?
Yes, Doctor.
Okay, so I owe you derivation and I owe you the questions, problem examples for single slit. I'm going to share it later so that you can watch it to solve for your quiz if you need it. Okay, so any other questions?
Can Doctor also talk about the summary of this chapter at the end of the video?
Yes, I will do a summary as well. So
Alright,
single slit, problem example, derivation, and summary. All right. Any other questions for me or requests for my video nanti? All the best for your quiz. No questions? Let's take a picture. This is our last class. Very sad. But I'm still your PA, so don't worry. Jom kita ambil picture. Turn on your cameras. Come on. Oh my God, you guys need a shave. Oh, Okay. Afika, Safrinas, Anis. Tak keluar gambar semua orang, tak keluar lagi. Kejap. Wow, gambar background Hajar. Kemain. Zul Hakim, Adlina, Amir, Balkis, Sarah Amani, Nurul Ain. Come on, is this our last class? I'm not that sad because I know I will see you guys again. Okay, tapi next semester you guys will have a new physics teacher. But you can always come to me. Okay, so my WhatsApp is available. Fatin Nabiha. Okay, dah ada. Khairun Nisa. Safrinas tak on pun. Nur Zulaika. Zul Hakim. Izu. Amir. Nurul Ain. Qurratu Alia. Safrinas. Okay, you guys ready? Okay, 1, 2. Kejap. Belum lagi. 1, 2. Say cheese. Okay, 1. Kejap, lagi seorang. Lagi satu. Lagi satu slide. Slide, lagi satu panel. Amir, Izu, Nurul Ain, Zulaika. Tak ada ke? Fatih Nabiha. Mesti tidur ni. Okay, one more time.
Saya punya kamera tak boleh
Oh, okay. Sorry. Saya tak bersangka baik. Okay, 1, 2, 3. Smile. Terkejut. Oh, okay. Again. 1, 2. Smile. Alright, got it. Okay. So I owe you guys a video and as usual, my WhatsApp is available. The group is available for you to ask questions as long as it's not on the quiz. For finals, boleh tanya soalan lagi Alright, so take care everyone. All the best for your quiz. All the best for your finals. I'll see you around. Bye.
Thank you, Doctor.
You're welcome.
Thank you, Doctor.
Bye.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Thank you, Doctor.
Bye.
Thank you, Doctor.
You're welcome.
Doctor?
Yeah.
I know it's a little last minute, but I have a question. It's about width of central bright, distance between m equals 1 and m equals -1.
Yes.
Yeah,
Good.
about that kan. It's in the module, and then they use y1 minus y negative 1, and understand because that's from the m kan. And then use 2. Is it because the 1 minus negative 1 gives you 2?
Because y1 is equal to y minus 1. It's equal, so that's why it's 2. Does it make sense, Belle? But I will explain it in the video. No worries.
Okay, thank you, Doctor.
Welcome.
Ira.
Doctor, for the wave in phase difference and path difference, at the first of the class about the graph, is it very important because it is not stated in the module? It is just in the slide. So do we need to memorize or just follow me?
I think it's in your quiz. Ada tak?
Say what, Doctor? Again, what about the quiz?
I think it was Mason Mason cakap, is it important to understand phase difference? Because it's not covered in the module, but it's in the slide. Well, the phase difference and the path difference forms your understanding for the young double slit and single slit interference. So I think it's important for you to understand it. You don't have to memorize it though. And I think it's on your quiz as well for chapter 12.
Thank you, Doctor.
Korang tak perasan lagi?
And thank you, Mason, for the question.
Alright, thank you, Doctor.
Okay, welcome. Apa Faiz?
Thank you, Doctor.
Okay, welcome. Bye.
Thank you, Doctor.
Welcome.
Thank
Bye.
you. Meow.
Mew. Faiz sudah apa ni? Era anja benda. Okay, bye.
Thank you, Doctor. Bye.
Bye.